Welcome back to The Explainer. Today, we're diving straight into one of the absolute most misused terms in engineering right now, the digital twin. Seriously, you've probably heard this thrown around in meetings, maybe seen it trending online, but the gap between the corporate buzzword and the actual technological breakthrough, it is massive. So, by the end of this, you're going to know exactly how to separate the hype from reality and how this architecture actually operates under the hood. Let's get into it.
Think about this for a second. What if a machine could literally tell you it's going to break down, say, 5 whole days before it actually happens? Now, I know, it sounds a bit like science fiction, right? Like some futuristic movie where machines are whispering their secrets to us. But the incredible truth is, this isn't sci-fi at all. It's a reality that's already up and running, right this second, in Tesla factories, inside those massive offshore wind farms, and even deep within the jet engines of the planes we fly on. And it's all thanks to the exact technology we're unpacking today.
Okay, so at its core, a true digital twin relies on a pretty strict foundational formula. It equals a physical system times live data times a virtual model. You absolutely have to have all three of these components working together. You've got the actual physical asset in the real world, like a robot arm or turbine. Then you have its virtual counterpart, the digital representation. But the critical piece here, the real multiplier that makes it a true twin, is that live data flowing continuously between them. Okay, let's dive into this master analogy. Honestly, the best way to picture this is to think of a digital twin as the Google Maps for a machine. Think about it. Back in the day, paper maps were just static pictures of roads. They didn't know where you were, they definitely didn't know if there was a huge traffic jam 2 miles ahead, and they couldn't give you a live ETA. But Google Maps, it's constantly fed real-time data from millions of sensors, our phones basically. It updates instantly. Well, a digital twin does exactly this, but for a piece of industrial equipment. It's just constantly fed live information about temperature, vibration, electrical current, faults, straight from the machine's actual sensors. Now, here's a concept that still trips up a ton of people, even veterans in the industry. It's understanding the crucial difference between the big three: the digital model, the digital shadow, and the true digital twin. Understanding this exact distinction is what separates the actual implementers from those who are, well, just riding the hype train. Once you spot the difference between these three, you'll instantly know who actually gets this technology. Now, what's really interesting is how we can break this down. First up, a digital model. This has absolutely no live connection. It's static. It's made once. Think of it like taking a photo. It captures a specific moment in time, but it never ever updates. Next, you step up to a digital shadow. Here, you get a one-way connection, straight from the physical machine to the digital model. This is essentially like a live CCTV feed. You can sit there and watch what the machine is doing right now, but you can't interact with it at all. Finally, we reach the true digital twin. This has a two-way connection between the machine and the model. It's like a video call. Information is flowing seamlessly in both directions. That two-way connection is the massive aha moment right there. And because of that two-way connection, a digital twin doesn't just watch the machine, it can actually talk back. If the system calculates and predicts that, say, a bearing on a motor is getting way too hot and is definitely going to fail, the twin doesn't just sit there and blindly send a warning email to some inbox. It can automatically act to slow that physical motor down, adjusting the real machine's behavior before the failure ever even happens. It's wild. So how is this architecture actually executed under the hood? I mean, it's one thing to talk about two-way video calls for machines, but it's another to understand the exact technical pipeline making it possible. Let's shift gears and look at how this information actually travels from the physical world of metal, grease, and electricity all the way over to the digital world of pixels and predictive algorithms. All right, here is the exact pipeline step by step. Step 1, it all starts on the physical machine, with sensors actively reading parameters like temperature, pressure, or vibration. Those sensors feed straight into a PLC, which essentially serves as the localized industrial computer right there on the machine. Step 2, that PLC packages up all the data and sends it out using specific industrial protocols. Step 3, the data lands in an edge computer right there on the factory floor for super quick decisions, or it gets beamed up to the cloud for heavy-duty processing. And finally, Step 4, all that processed data is fed into a simulation engine and a visual dashboard where a human operator, or increasingly an AI, can analyze the whole setup in real time. Now, the absolute lifeblood of this entire step relies on industrial communication protocols, specifically things like OPC-UA and MQTT. Simply put, these are the standardized languages that allow different localized PLCs to exchange data securely and super efficiently, pushing it up to the edge or the cloud.
The PLC on the factory floor basically speaks this exact language so it can smoothly talk to the rest of the advanced digital network, ensuring zero data gets lost in translation. Let's move on and see how this builds out in a real-world scenario to make it incredibly concrete. Imagine a complex industrial robotic arm, something like a UR-10E, working tirelessly on a manufacturing assembly line doing rapid pick-and-place tasks. Now imagine its exact virtual counterparts running in a highly accurate physics simulation engine, like NVIDIA Isaac Sim. We've got our physical asset moving in the real world, our virtual model mimicking it flawlessly on a screen, and that crucial live data linking them completely together. Consider a factory without a twin for a second. A bearing inside that physical robotic arm starts to overheat. Nobody knows, not until the arm completely seizes up unannounced, production halts instantly, and boom, you have ruined products and lost revenue. Now contrast that disaster with a twin-enabled factory. The temperature trend is being continuously watched by the virtual model. It spots the anomaly instantly, predicts the failure, and allows the team to simply schedule maintenance during off hours. Production literally never misses a beat. The exact timeline of this predictive maintenance typically plays out over a really brief, critical window. Think of it like this. On day 1, everything is running normally, green lights across the board. By day 3, the physical sensors detect a microscopic vibration and some tiny temperature spikes. Honestly, nothing a human standing right next to the machine would ever notice. But on day 4, the virtual model, which is crunching this live data against historical physics, raises the red flag and predicts an imminent failure. And on day 5, before anything actually breaks, the maintenance team swoops in, replaces the part, and resets the system. The operation effectively saw the future and changed it. How cool is that? While predictive maintenance and drastically reduced unplanned downtime are for sure the massive headliners that save companies millions, the benefits actually go way beyond just stopping breakdowns. You unlock virtual testing, so trying out a brand new risky robot program in the simulation before you ever risk crashing the super expensive physical asset. You can dynamically run energy optimization to save power across an entire global fleet. And you can manage that entire global operation remotely from a single dashboard anywhere in the world. It is a total game changer. Now, because this technology is so incredibly powerful, the term is frequently misused by companies just trying to sell basic software products. It happens all the time. So it's time to pick up the pace and bust some of the most common industry myths right now, so you can sound like a true insider and properly evaluate these systems in the wild. Let's cross these off. Myth number 1. A 3D CAD model is a digital twin. Absolutely false. As we know, without live data flowing into it, it's just a static model, not a twin. What about the idea that IoT is a twin? Also false. IoT is simply the network collecting the data. The twin is the intelligence that actually utilizes it. Finally, the myth that every single simulation is a twin. Again, nope. Without live synchronization to a physical counterpart, it is really just a standard simulation answering hypothetical what-if scenarios, rather than responding to what is actually happening right now. So the crucial point really boils down to this tasty analogy. IoT is one ingredient, the twin is the whole dish. If you were building an advanced manufacturing setup, having sensors collecting data is basically like having flour, sugar, and eggs sitting on your kitchen counter. I mean, it is totally necessary, but it is definitely not a cake yet. The digital twin is the finished, baked dish that actually provides the value, the insight, and the predictive power. So I want you to look at your own operations, or the systems you're working with right now. Is your digital setup just watching you like some glorified CCTV camera? Or is it actively predicting the future and ready to act on its own? A true digital twin fundamentally changes how we engineer our world. And honestly, we are really just scratching the surface here. Next time on The Explainer, we're going to dive deep into the AI layer that actually makes these exact predictions possible. Until then, thanks so much for joining me, and I'll catch you in the next one.